This is PreCalc 11, Chapter 7.1. We're going to be looking at equivalent rational expressions. This is another example of why factoring and finding zeros are important in rational expressions. And recall that x over 0 is undefined. A rational expression has the form p of x over q of x, where p and q are polynomials. Recall that polynomials have non-negative exponents for the variables. So here's an example. This is a quadratic over another quadratic. This is a cubic over a quadratic. All the exponents are integers and positive. And just like we have equivalent forms of fractions, 1/3 equals 2/6 equals 3/9, we have equivalent rational expressions by multiplying or dividing by a common polynomial factor in the top and bottom. So if we multiply this by x minus 3 over x minus 3, we're multiplying by 1 because anything over itself is 1. And we want to add brackets here to make everything clear that we're multiplying a polynomial by another polynomial. Here, we can make another equivalent rational expression by multiplying by constants. 4 over 4 is 1, so we're not changing the expression. And here's the note. Notice that we add brackets to make it clear that we're multiplying the polynomials. We're not multiplying 2 by x minus 3, we're multiplying this whole polynomial. And let's look at another one, x squared plus 3x plus 2. We can make this an equivalent rational expression by factoring. This is x plus 2 over x plus 1, and the denominator is x plus 1 over x plus 1. And we can cancel these because they're exactly the same, and we get x plus 2 over x plus 1. Remember, we need to cancel the same number from the top and bottom. Just because these two are identical doesn't mean we can cancel this one out as well. If there were 2 of these factors in the top, then we can cancel them all out, but there's only 1, so we can only cancel one of them in the bottom. Now, whenever we use rational expressions, we need to check for non-permissible values. Okay, for equivalent rational expressions, we may add additional non-permissible values, but we never remove any of the original non-permissible values. And the non-permissible values are simply the zeros of the denominator. Remember, we can't have something divided by 0. So here we have x plus 2, x plus 1, over x plus 3 times x plus 1. Okay, again, the x plus 1's cancel out. We get x plus 2 over x plus 3. And the NPVs originally are x equals -3 or x equals -1. So we get the -3 from here, we get the -1 from here. And when we've reduced this, our NPVs are x equals -3 or x equals -1. Okay? We can't remove any of the original NPVs. And note, there may be a temptation to cancel incorrectly. So only cancel when it's fully factored. So there's a temptation to do this. I see a 2, so I cancel it out. But this 2 is being multiplied by the x, and we have terms here. So we can't cancel it out. Even if we did this, we still can't cancel it out because we need to cancel something out from every term. So incorrect. And x does not equal -2. And again, this is incorrect because it's not fully factored. Now, if we look at something like this, we factor 2x plus 1, and we factor 2x plus 4. We can go ahead and cancel this out, and we get x plus 1 over 2x plus 4. So this is correct. Now, it's important to say the non-permissible value is. Here, we're not saying NPV. This is the domain. The domain is x does not equal -2. So if you want to be explicit, you can put domain here. So please specify whether you're stating the domain or the non-permissible values. Now, even if a question does not ask for non-permissible values, you should get in the habit of stating them anyways. And to get to the simplest form, you must fully factor. Monomials can look complicated, but they are actually the easiest to simplify because they're already factored. So let's look at this one. We have x cubed over x. We cancel one out of the x's, and we cancel the x from the bottom. There's a y squared, so this cancels out. And we have z squared, and we cancel the 2's out. So we're left with 8x squared. All these are gone. Only the squared is left, over 2z squared. And we can cancel further. We can cancel a 2 out of the top and bottom. And we get 4x squared over z squared. So we get the original NPVs. None of these can be 0. So x, y, z does not equal 0. Okay, and if you want to do it the other way, that's the domain. The NPVs, x equals y equals z equals 0. Okay, let's look at this one. Let's cancel out a 7. We're left with a 2. Cancel out an x, so reduce that by 1. Cancel out a y, so reduce that by 1. And cancel out a z, reduce this one by 1. So we've canceled everything in the top. It's important to remember that when you cancel everything out, you're left with a 1, not a nothing. So this is 2xy squared z cubed, and x, y, z does not equal 0. Okay, and remember, canceling results in a 1, not nothing. The discriminant can also be used to determine how many NPVs there might be. So here's an example. Let's look at the denominator. B squared minus 4AC equals 0 minus 4 times 1 times 9. And this is less than 0. We don't care about the value. This is minus 36, but we just care that it's less than 0. So there's no zeros. Therefore, no NPVs. And this symbol is therefore. And again, it's important we say NPVs x equals 0. And we don't say NPVs x does not equal 0, or whatever the NPV might happen to be. So, and for domains, we say x does not equal 0, or whatever the value is. The domains are the permissible values. So the domains and the NPVs are opposite. So if we look at here, we have the domain x, y, and z are not 0. The NPVs are the opposite. So x, y, and z are 0. Okay, rational expressions are equivalent if they have the same domains or NPVs. They aren't considered equal even though we use the equal signs. And that completes this lesson.